How can we read the world through function graphs? Have you ever seen a line graph showing how the temperature changes in a weather forecast? Stock prices and height growth are also usually shown with graphs. Why do people use graphs instead of long lists of numbers? Because graphs show change much more clearly than numbers. A function determines one value from another. However, it is not easy to picture a function by looking only at its equation. Does the output increase as the input increases? Does it start to decrease at some point? Where does it reach its greatest value? It is not easy to answer these questions from the equation alone. That is why mathematicians began to draw functions as graphs. The French mathematician René Descartes made this possible by introducing the coordinate system. Coordinates made it possible to draw functions that had been expressed only with numbers. They also made it possible to express figures with equations. The field that connects numbers and figures in this way is called analytic geometry. The functions we encounter most often are linear, quadratic, and trigonometric functions. A linear function forms a straight line. A quadratic function forms a parabola. And a trigonometric function forms a repeating wave. The shape of a graph alone reveals much about a function. Just as a face reveals an expression, a graph reveals a function's key features at a glance. For example, if the graph rises, the value increases. If it falls, the value decreases. The highest peak is the maximum value, and the deepest valley is the minimum value. The definitions of local maxima and local minima may seem difficult in a book, but they become much easier when viewed as peaks and valleys on a graph. Graphs also help predict the future. The distance traveled by a car moving at a constant speed and the length of a stretched spring can both be modeled by a linear function. A linear function is uniquely determined by 2 points. In other words, measuring just twice is enough to predict all the remaining values. The braking distance of a car and the path of a ball thrown into the air can be represented by a quadratic function. A quadratic function is determined by just 3 points. This means that only 3 measurements are enough to predict how the shape will change. That is why scientists and engineers use function graphs to analyze many phenomena. Mathematics also places great importance on existence and uniqueness. The first step is to determine whether a solution exists and, if it does, whether there is one solution or many. A graph is the easiest tool for doing this. For example, imagine 2 cars traveling at different speeds. To find out whether they will meet, represent each motion with a function and draw the graphs. If the graphs intersect, the cars will also meet. One intersection means they meet once, and 2 intersections mean they meet twice. If the graphs never intersect, no matter how far they are extended, the 2 cars will never meet. A function graph is not just a picture for solving math problems. It is a language that reveals trends, predicts the future, and even shows whether a solution exists. We use graphs to describe countless phenomena, from changes in temperature and economic growth to AI learning and spacecraft trajectories. Reading graphs is, in the end, another way to read the world.